In this video, we're looking at example 8 in section 8.3. So for example 8, we're going to use the limit comparison test to test each of the following series for convergence or divergence. And then we're going to write a formal proof to justify our answer. So in this video, we're going to cover part A. So to get started, I just want to start off by doing a little bit of scratch work here, because the limit comparison test can sometimes be a little bit involved. We have to play around with it a little bit because we need to find that a to the n series to compare ours to. So we'll just call this scratch work. Okay, so our series has the terms 1 over 2 to the n minus 1. So we'll call that the b to the n. Okay, so now we need to find an a to the n sequence to compare. So what we saw in the last video was that these terms here look a lot like, where's my pointer? Just 1 over 2 to the n. We can kind of ask if we, squint our eyes or step back or look at the dominant terms here. Well, we have 1 over something. What does that something become? Well, 2 to the n kind of dominates. So let's see if that sequence, a to the n equals 1 over 2 to the n, just 2 to the n, can help us compare with our series to determine its convergence. Okay, so here's our testing series. So let's just take a look at that series real quick to determine if it converges or diverges. And we saw this in the last video, but I just want to make a note so it's really clear. So this series 1 over 2 to the n, so that means our a to the n series, is convergent because it's a geometric series. Geometric series with r, the common ratio, equal to 1 over 2. Okay, so here we have our test series. It might not be the one that we stick with, but we're going to try it out. It's our test series. We know that it converges. So if we're able to compare it with the series of the BNs, then we can determine what the BN series does based on what the AN series is doing. Okay, let's go ahead and set up that limit. So we need to consider the limit as n goes to infinity of Bn over An. So let's write out what that looks like. So that is the limit as n goes to infinity of, I'm going to write a different color here so it's clear what our Bn is. Bn, which is 1 over 2 to the n minus 1, divided by our An, which is 1 over 2 to the n. So now I'm dividing fractions. So how I divide fractions is to multiply by the reciprocal. So if I have the limit as n goes to infinity, this becomes 1 over 2 to the n minus 1 times 2 to the n over 1. Okay, so just doing a little bit of algebra here. So that becomes the limit. And notice how I'm keeping this limit notation throughout because I haven't taken the limit yet. So I need to make sure that it's clear that I'm computing a limit still. So in the denominator of 2 to the n minus 1 times 1. Oops, I dropped my minus 1. Oh, I didn't drop it actually, it became an exponent. So let's just make sure that's clear. Minus 1 here. And then we have minus 1 there. Okay, so what is going on with this limit? So we can notice as n goes to infinity, that numerator goes to infinity, and so does the denominator. So we're going to go ahead and use L'Hopital's rule. And that allows us to state that this limit is the same thing as the limit of the derivative of the numerator over derivative of denominator. So side note here, how do we compute the derivative of a function that looks like 2 to the x? So notice x is not in the base, x is in the exponent. So this is not a power rule derivative. The formula for this we met in Calculus 1 or Math 151. The derivative is 2 to the x times ln of 2. And this is done using a technique called implicit differentiation that you should have seen in Calc 1. So I'll just say, if you want to kind of review that a little bit. See your Calc 1 derivatives. Okay, cool. So what does that mean for us? Well, let's go ahead and compute those derivatives of the numerator and denominator then. So the numerator derivative would become 2n times ln of 2. The denominator would also be 2 to the n times ln of 2, and then minus 0. So that just goes away, which is really nice for us because this is then just the limit as n goes to infinity of, well, we have the same numerator as denominator, so these cancel each other out to give us just 1. So the limit there is equal to 1. So if we look at that limit comparison test, what we just found was that the limit of the ratios of the terms in the two series is equal to 1. 1 is positive and finite. So that means the behavior of the a to the n series is the same as the behavior of the b to the n series. So we'll summarize that here. So 1 is positive and finite. So what's our conclusion? So sometimes we use 3 dots in math to mean like therefore. So therefore, since the series of a to the n converges, so does the series of the b to the n's. Okay. So there's our scratch work. So we see that what we found or showed is that we could find a series, and that's the sum of 1 over 2 to the n. We know that series converges. When we compute the limit of the ratios of the two terms in the series, we get a positive finite number. So using that, we'll write out that theorem here so we can use it in our formal proof. So using the limit comparison theorem, or test, we could call it a test or a theorem. We'll just say LCT. That means that we get this result, that the b to the n series converges. All right, so now we're all set up to write a proof of this. All right, so we need to make our conclusion using a nice succinct argument in complete sentences. So we can say, since the limit as n goes to infinity of the b to the n's over the a to the n's is equal to 1, is positive and finite. Very important, needs to be positive and finite. And since that series we compared to, and since the series of the a to the n's, which we used as the series of the sum of 1 over 2 to the n, is convergent, and we could even say specifically is a convergent geometric series. That gives justification for why it's convergent with r equals 1/2. That means the series of b to the n, which for us was our 1 over 2 to the n minus 1, also converges. And that is our formal proof. And now we can just check that we have included everything. So have we written complete sentences? Yep, check. Have we used proper notation? We can check through. Yes, we're being really clear about what our two series are, that we're taking that limit. So we're setting up that theorem correctly. And are we using the theorems appropriately? Maybe not. Maybe I should include a little bit more here. So we might want to say this series also converges. How do we know? By the limit comparison test. There we go. So now we've included what theorem or fact we are using to justify that final result. All right, great work working through this. In the next video, we'll see another example in part B.